skip ಹೊಡಿಲಲ್ಲಿ audible audible ಸ್ಟಾರ್ಟಿಂಗ್ ಮಾತಾಡಿದ್ರೆ ಕೇಳಿಸ್ತಿಲ್ಲ ಹಿಂಗೆ. Let me again try. Okay, I just found the confirmation. So okay, so no issues. So I think I'll be audible, so my screen is visible. So just a minute, I'll wait for another minute so that few more members can join here. ಅಂದ್ರೆ ಡಿಲೇ ಅಷ್ಟೇ ಐತೆ ಖರೆ, ಇಟ್ಸ್ ಫೈನ್. ಯಾವ ಸ್ಕ್ರೀನ್ ಕಾಣೋದು ಅದೇ. Shall I start now? Okay, so well, let's start with the session, guys. So I'm here with the third session on free master course on structural analysis, NVH, crash, and durability. So for information, to just to summarize, so in this session one, we had gone through the basics of CE and what and all the job opportunities are available. So how we need to prepare ourselves on the CA domains. So what are the domains available? So these things we had seen in the session one. And in the session two, we just explored the basic simple tool that is SolidWorks simulation to just to know about how exactly we can start the simulation inside the tools. Okay, if we directly try to explore the ANSYS, HyperWorks, and pre-processing and the post-processing tools, it might be difficult for each and everyone to grasp it. So we started with the simple tool, and which is also known for industrial equipments and the small scale industries, the SolidWorks simulation. So we just started with that and just seen how we can set up the basic structural analysis into that, and we had seen also the basic frequency, that is modal analysis, into that. Yeah, in the today's session, I'll be focusing on a basic structural analysis on one of the component, a kind of a link we'll consider, and we'll try to check how the component is uh, working on the given boundary conditions, and we'll try to give the validation for that, and then we'll focus on the buckling analysis and the introduction to buckling analysis. Also, we'll see how exactly we can interpret the results with the numerical problems. Yeah, well, let's get started with this. So first thing, we need to know about the buckling analysis. So what exactly the buckling analysis is. So in short, you could see the definition here. It just refers to a sudden large displacements due to the compressive loads. So the buckling will happen only for the compressive loads, not for the tension, okay, expansion. So we won't have that buckling there. So this is if we have the compression in the model, what will exactly happen is, due to that load, sudden slenderness will happen, sudden failure will happen in the model. So due to axial loads, no, that will happen. So that we call it as buckling. Okay, so you could see one more thing. A slender structure subject to axial loads can fail due to buckling at the load level lower than those required to cause the material failure. In short, if your material is fine for that model, even though due to the geometrical variations, the model will buckle. Okay, that is important here. Now, so you need to remember, so while doing the buckling analysis, so we try to extract the mode shapes. So in short, we try to run model analysis, and we mostly consider the first mode as a critical load or a critical mode shape for the buckling if the component is going to fail. So we can consider that mode shape as a reference, and we can see the location where it is trying to buckle and try to improvise it. So that is the best way to identify the buckle. Okay, I hope this is clear. Let's see the next slide. So this is about the explanation. So what are the eigenvalues? So from that, what exactly extract the mode shapes, and then what exactly do in nonlinear buckling. Okay, so for information, whatever the linear buckling we are going to do, it is not exactly related to the any of the material properties, and it is just a scale. Okay, whatever you're going to extract from the buckling analysis, it's a mode shape. Okay, and you're gonna get the buckling load factor for that particular component, and that is not 100% accurate. It is here and there. Okay, we can consider 35 to 20%, slightly near to the non-linear buckling analysis. So we always prefer to do the non-linear buckling analysis if you see the component is trying to fail in the buckling in the static analysis. So even though if it is not failing, so we always recommend you to consider the non-linear buckling to validate your components. Okay, if your component is prone to buckling, okay, that is important. If you consider the automotive industries and the medium scale industries, this is very important. We try to consider the critical load. So there will be like the working condition for the medium scale industries, certain value, let's say, assume it is 32 kilonewton. The model is perfectly fine and it is not buckling. And we also need to take the critical loads like the F2, we call it as, so SEME load cases. So it is 10 to 20% more than the whatever the load you have considered. Assume the F1 load is 32 kilonewton, and we also need to try to validate it for the 20% more than that load. Assume it is on an average you can consider 40 kilonewton, so that should also pass. So there shouldn't be any of the plastic deformation in the component due to this F2 load case. Okay, well, so this is just for information. So what we do exactly at the back end, yeah, as a C analyst, so we try to check these all the things, and we always have a buffer. Okay, well, so just to get into deep about the linear and non-linear buckling, so you could see we have two scenarios. If you want to do the buckling analysis, you can just simply carry out the linear buckling analysis, that is a linear eigenvalue buckling. Okay, in short, this is the formula we use it. Okay, and then what exactly it does is it will try to give us the buckling load factor. Okay, and also the mode shapes. So what we can do is we can just multiply the applied load by the buckling factor, will get us the critical load. Okay, so for example, assume you have the model. So what you can do is you can simply apply the unit load, and then you want to get the buckling load factor. That is the exact critical load. Okay, that I'll anyway showcase in the live demo. We'll see that one. So what exactly it does is it shows the buckling modes in a faster manner. Sometimes it overestimates. So that is what we say, linear buckling is not that accurate. So for that we try to do the non-linear. So it assumes the model is perfect geometry and it is a linear material, so it overestimates the loads. Okay, that is important. So don't believe the results of the linear buckling, in short. That is what I would recommend. Next, what exactly we do in non-linear buckling? So in non-linear buckling, we try to consider the geometry non-linearity into account. Okay, so let's say you already know about the engineering stress versus the true stress, right? So if you go through that, you'll get to know what is geometric nonlinearity. Okay, and then the material nonlinearity also, stress strain curve will take it. Okay, then so with respect to the incremental risk and arc length of the method, so these are the methods we try to extract the nonlinear buckling. So what exactly we do? So it includes the initial geometry imperfections. Let's say if your model has some of the sudden slenderness, or it has the necking regions, that it will consider into account. Okay, and then it will try to give the mode shapes on that particular region so that you can easily predict where exactly buckling is going to happen. Next, it will also use the nonlinear geometry. So it will consider the large displacements into account, and it will try to give the results accordingly. Okay, next, uh and it will also consider the nonlinear material. So if you try to do the analysis in OptiStruct nonlinear, so I can even show this how exactly we consider the geometry and the material nonlinearity into account. Next, very important is this one, use of the control arc to capture the post buckling and the limit points. Let's say once we do the validations by using the material and the geometric nonlinearities, we'll draw a curve. Okay, with that curve we'll get to know how exactly the buckling is happening, at what load case, and at what displacement it is happening. So how much is the a load factor it is considering. Let's say my model needs to pass exactly 50 kilonewton. If it is not passing for that, so what we try to do, so these all things we can predict it by using the post processing. So whatever the results you're going to get from the nonlinear buckling, no, so it is more realistic critical load and post buckling behavior. So this is 100% accurate compared to this linear buckling. Okay, so I hope the difference is clear. Well, let's see the next slide. So this is the formula for the buckling. So that is, we call it as Euler's buckling formula. So if you consider this, so critical buckling load factor, which is equal to pi square EI divided by KL whole square. Okay, here E is the Young's modulus, I is the moment of inertia. So K is the constant we consider, endpoint constant. So I'll show you what and all the constants we have it. So how we use it. Next, L is the length of the geometry in short. Okay, well, so if you see this one for this constant, so these are the values we considered with respect to different boundary conditions. So let's say if you have the pin to pin conditions, we consider K which is equal to 1. Okay, and now here one end is fixed. Okay, assume this end is fixed and one end is, this is free. Okay, fixed and free ends. Okay, now here we consider it as 2. Next, both the ends are fixed conditions. We apply the load. In that case, we consider 0.5. Next, pin and fixed. We have the rotation here, but one end is fixed. That time we consider 0.7. So these are the constants we take it into account. Okay. Well, so now very important thing is the buckling load factor. So what exactly it is? You could see the definition is the number by which the applied load must be multiplied in order to obtain the buckling load magnitude. For example, I would like to have this critical load, that is the buckling load magnitude. Assume this is the formula, buckling load factor, which is equal to critical load divided by applied load. So that time what you can do is applied load you can consider unit 1. You can just multiply with the buckling load factor. Now you'll directly get the buckling load factor, which is equal to whatever the load you have applied. So accordingly you will get the results. Yeah, we'll see this one, how we can get the results and how we need to extract the buckling load factor. Okay, now as I said, non-linear buckling analysis must be used to find the accurate values of buckling load in many cases and to do the post buckling effects. Very important. Yeah, so in short, what exactly we gonna get it from this one. So the model analysis provides the quantitative information about the mode of vibration, but not the actual magnitude of the displacements. So you're going to get the mode shapes, that's all. Okay, it is not exactly the magnitude of the displacement in the linear buckling with respect to whatever the factor you're going to consider here. Well, this is very important. So if you get to know about this particular chart and you're well known about the buckling results, the first thing is buckling load factor. If it is greater than 1, greater than 1, your component will not buckle. Okay, so applied loads are less than the estimated critical loads in short. So whatever the critical loads you have it, so if you get the buckling load greater than 1, so your model is satisfying the buckling conditions, it is not going to buckle. If it is 0 to 1, if it is in between this, then definitely your component will buckle. So it exceeds the critical applied loads. If it is equal to 1 also, the critical load and the applied load are same, then it is definitely going to buckle. Okay, remember that. If it is -1, there is no buckling. Okay, what exactly it shows is buckling occurs if you reverse the all the load direction. So in short, assume you are applying the tension load, okay, kind of thing. Next, -1 to 0, there is no buckling. Even it is less than -1 also, there is no buckling in short. So assume if you are buckling load factor is greater than 1, in short it is not going to buckle. If it is less than 1, then definitely it's going to buckle, okay. And now, very important thing is you should not take only one as a reference. Sometimes, as per the factor of safety, some components will have the buckling load criteria is should be 4 or 4.5 or 6 or 2.5 or 3.2, depends. We don't know. So we need to consider that. You need to ask what is the buckling load factor standard for this model. If they say it is 1, consider. If they say some other value, please try to take that into account. Okay. Yeah. Next. Now, we'll consider this example into account. So we have the numerical results also for this, and we'll try to simulate in the solver by using the SolidWorks simulation tool, and we'll check how it is correlating, and we'll also test few models. Okay. First thing is the formula, we already seen it. Okay. So if you take this formula into account, the pi square here, EI, Young's modulus 210 gigapascal, and then I is the moment of inertia. Put this particular formula and try to find out this one. So this is the radius, and this is for, okay. And then next we have K factor, okay. It is one end is fixed, I'm considering, on another end I'm applying the load, so it is K is equal to 2 here into 300. 300 is the length, square. So if I put this values and all the inputs, I'm getting the value as 45.15 kilonewton as the critical buckling factor. So BLF, okay, for me it is this 45 kilonewton, okay. Now what we'll do is we'll try to assimilate this one in short and try to check how exactly we have the correlation. So let me just do that. I'll switch to the SolidWorks tool. Okay, so now I'll just directly open the part. What I'll do is I'll start from the scratch. Before that, I'll just switch to white plane. I'll use the top plane. I'll just draw a circle of diameter 20 as the radius is 10. And then exit the workbench, isometric view. Try to extend this. I'd like to have the value as 300 mm. And it has not changed, right? It shows your rebuild. So just press Ctrl B. Now this is what the example is, okay. Now I need to do the simulation. So if your add-in is not turned on, you can switch to SolidWorks add-ins. If you don't get it here, you can use this drop down, check here, SolidWorks add-ins. So here you can just activate your add-in. If you want it at the startup also, you can have it here. Every time you open the software, it will be activated. Or else if you want to manually open it, you can come and check this option, so that if you have the SolidWorks license, this will work, or else it won't work. For information, remember that, okay. If you are using the SolidWorks CAD standard tool or a professional, you might not get it even premium. So if you want these options, you might need to purchase simulation packages. You can cross verify with your, yeah, whatever the manager, whatever it is. Now I have the simulation tab activated. What you can do is, now this is the icon, there's a new study, okay. You can just click on this. Now what exactly analysis you want to do, you can just mention it here. So I would like to keep it name as buckling 1, fine for me. So you could see I have all the analysis into account. So as I'm using the premium license, so now it is SolidWorks simulation premium, okay. I would like to do the buckling analysis. You can select it here, okay. Once you select it, just click on green check. You have the buckling analysis tab open. Here you have the window that is design tree to work on it. Now I need to, first thing is apply the material on this. What you can do is you can simply right click and go to edit and apply material. and check for the material. So right now I would like to go ahead with the alloy steel. Here you could say it is Inks modulus is 210 gigapascal. If you want to change it, you can just change it to megapascal. And if I take the IPS, it is in PSI. So now I'd like to go ahead with this. Now apply. So in short, we have applied the material. It shows the green tick on it. Now the simple model, there's no connections or contacts here. I can directly jump to the fixtures. So here I would like to define the fixed geometry on one face. This is the reference. So this face is fixed for me. Okay. Now, application of load. You need to remember the load, whatever I'm going to apply here, is not going to matter for me because it's just a unit factor here. And I just want to extract the buckling load factor. So to get the buckling load factor, so I need to have the unit value here. The value I should define it as 1. So if I multiply 1 into BLF, so anyway I'm going to get the buckling load factor. So whatever the critical load I'm going to get it, it will be visible with respect to this analysis. In short, what I'll do now, I'll apply the force on this face 1 Newton. So it is unit value. So in short, it is 1. Now, so if you want, you can mesh it. Let us mesh this model. Let's try to use the fine mesh. You'll have to use the curvature based, or else blended curvature based is also fine. So this is very fine mesh. Okay. Now we'll try to run this. So just right click and just run. Okay. Yeah, with that we have the result here. This is not needed here, but here if you see, the buckling load factor is 45 kilonewton in short, right? 45,210. And if you see the presentation also, I'll just switch back again. You can see it shows 45 kilonewton. So for the simple models, the numerical value as well as the analytical values, so we are getting simulation values, we are getting similar. So in short, we are doing good, correct? Now, this is one example. So let us do one thing. We'll do another complex model analysis so that you can understand in a better manner. So let me start take the new model. So I'll open the desktop. So I'll consider the models here. The mechanical link, I'll take this. So I would like to, nope, simply right click and break the link. Yes. And you can check for the import diagnostics. There's no issues with the model. Now, this is the model. First thing what I would like to do is I would like to do one simple structural analysis, static analysis, to see whether the model is fine or not. So for that, I'll start with the new study. Okay, so here I'll consider this static analysis. I'll just click OK. Now the material, I would like to apply the alloy steel. If it is there, you can just consider, or else you can just click over here and apply. Okay, this is done. Now I would like to define the boundary condition fixed for this particular phase. And these tools, it is very easy to define this one, but in advanced tools like the ANSYS, HyperMesh, pre-processing, there are a lot of work we need to do this, all the boundary conditions there. Now I have fixed this phase. Now the load, I would like to consider the force. It should be selected direction. like to consider this face, means this as a plane reference, and here if I consider this face, yeah, this is fine here. Let's assume again, if I take one, let's see. Okay, no, I don't need to do here. Let's define it as 500 Newton. Reverse the direction, so I need to compress this model, right? So yeah, this is perfect. Now I'll need to mesh this model. I'll go ahead with a slightly fine blended curvature. This time I would like to use 3. Grain check. So here I do need the curvatures. I don't need to do the geometry cleanup on this model because due to the buckling or due to the load cases here, we might get the stress hotspot. So we should have the curvature radius there. Yeah. Now this is fine. I need to run simple run on this. I'll simply run the structural analysis, static one. I could see the one masses stress and the different values. So what I could do here is I'll just edit this chart to the maximum. I can have it here. It should be in megapascal. Apply. In short, the model is 27 megapascal. It's fine in short, but the displacement is exaggerated. So you can even try to set it to true scale so that you don't see that particular big uh, deflection. So for this also you can go and edit the definition and you can have the true scale. Yeah. So in short, if you try to have this kind of load on this model, this is the critical region. So now we got to know how it is happening here, and the plastic strain at this region is, it is not even 2%, 0.2% also. So this model is completely safe with respect to 500 Newton. Now I would like to create a new study. You can go ahead with the new simulation study. This time I would like to do the frequency analysis on this model. Just screen check. Okay. If you want, you can use the fixed boundary condition on this. So if I don't apply the picture here, it again the first 6 degrees will be free. Okay. Yeah. So now I'll simply run the frequency analysis, or else I can even try to apply the load. Let me see. So let me consider the plane and this direction. Let us see with respect to 500, this face and this face. So here it is not the torque actually. So it should be total. A minute. Okay. These two are the faces. Here the selected direction is this. Yeah, this is perfectly fine. You can reverse the direction. Yeah. So I have applied the loads. Let me just run this. Okay, sorry, material is not defined. Can go here and apply the material as alloy steel. Apply this. Now can even try to set up the mesh. Let me just quickly do that. Blended 3, green check. Meshing is done. Now run this. So in short, it is trying to solve the frequency analysis for this model. So now you could see this is the first mode here with respect to this particular load case. So it is not a free model. So with respect to the load case, what I have applied, it is showing the results. So I can animate this also. So this is how it is going to bent for this particular load. In short, it is not going to buckle here. Okay, and then if I see this load case and if I animate this, it is trying to buckle here. This is also not critical for me. It is 1113. It is not going to happen. So this is also not possible because again it is deflecting some other regions. So my load case is exactly straight, so it is 1600 hertz. So I don't think so there I'm going to have this kind of scenarios. Okay, in short, you could see as per the rule, the first mode is perfect. Now here what I can do is I can simply delete this load case, and let me also delete the no, let it be. So let's try to run with the without load case. Okay, we have the boundary condition where we try to fix this, and with respect to this fixture, what we are going to get it. Ensure that is the same. Okay, okay, so now what I can do is I can even show you guys what we can do is we can simply even remove the fixture and directly run this with respect to free. There's no boundary conditions at all on the model. Okay, so this is the same issue which we got it last time. So I need to delete this complete model and I need to redo the frequency analysis on this. So I'll simply first apply the material here and then I'll run this directly. Okay, so here the first 6 are 100%, it is 0, so I should have at least 8 or 7 to have the results. So what I'll do is I'll again rerun this. Okay, still the same problem. I need to rerun this. Click OK. So here, before running it, you go to the properties. As I'm running the free analysis, I would like to extract the 10. Then apply the material again. So this one, close it and run this. Okay, turning on shift flag. Okay, so there's again a problem with this. Okay, so there might be some issues with the solver or whatever it is, so we'll just try to skip this one. So anyway, we just wanted to run the uh, free more analysis. With that, we wanted to check how it is going to be here. So no issues. So we got to know somewhere it is going to buckle at this region with respect to this load case if from the buckling. Now we'll try to run the buckling analysis on this model. So what I'll do is I'll again start with a new study. This time I'll directly go to buckling. Okay, I'll click on OK. Now what we can do is we can even copy and paste the load cases. Let's say I would like to have this one and this loads. You can just try to copy and here you can paste it. Paste. Here if I click it and here it is pasted. So you don't need to apply it again. So it's a shortcut in SolidWorks. Okay, now the material I'll apply. The mesh also can bring it from there, but it is quite simple, so I can even apply from here. Green check. Now instead of value 500, I would like to take unit value here, so that I would like to find the what is the critical buckling load factor, so that if I apply that directly, then I'll get to know where exactly it is buckling. So I could say it is 49 kilonewton in short. So this much value I could define it here so that it can buckle. The buckling will happen exactly the same we had seen in the the animation, right? Now, what I would like to do here is we'll try to make some changes into the geometry so that we'll see how exactly it is going to affect on the model. So what I'll do is I'll go back to the modeling. So here, mm, I'll just select this front face. On this front face, I'll simply draw a sketch. Okay, and let me just draw here also. So what I'll be doing is I'll try to remove this material, both the sides. You can select through all both, green check. Now in short, we artificially induced the slenderness in the model. Now we'll try to run this again. It got reduced to 25. Before it was on an average 40. If I even see this results, the stress value got increased to 82, and this is the critical region here. Yeah, and one more important thing is this is not considering the geometry and the material nonlinearity into account. Actually, means my assumption is if you have this load with respect to nonlinear buckling, the buckling should happen here, but with respect to the prediction, it is trying to move this region. That might not be correct sometimes, so that is also one scenario I could consider. So for information, you need to know this. Yeah, so what we can do is, let's do one thing. We'll try to change the load here. Instead of this value, would like to have it as 20 or else 50,000. Okay, and now you run this model. So even with this also, you're gonna get the same buckling, but the load factor got reduced to 0.5. Anyway, it is going to fail in short. Okay, yeah. So now from this, what I could predict is uh, the linear buckling might not give you the results what we are looking for. Sometimes we might need to run the nonlinear buckling to get sometimes the exact results. Okay, yeah. So now what we'll do is we'll take one more scenario into account finally. So I would like to consider one of the automotive component. So we have this car suspension. Okay, I could say this model just for the learning purpose, educational purpose. I'm just using it. You can just download this model from the internet. Okay, now assume I would like to consider this link. It might be the links chassis components. So you can simply select this one here. You can open this separately. Before that, you need to break the links. So once you break the link, now it is separate. You can right click and open it separately here. Now try to run the import diagnostics. The model is perfectly fine. Now quickly switch to simulation. Here I would like to fix this region. Buckling only I would like to do it here. Then fixture is this. Green check, and then I'd like to apply the load. Before that, I would like to have one more fixture on this. So in this scenario, I'd like to have the sliding. So if I select this face, the advanced option, I would like to have the flat surface. This here, this should be, I would like to keep these two 0, and this should be working in short. I can even remove this. I can select these two faces also as a reference. I think it is not a flat surface. Okay, let's consider this. You could see we have fixed z and y direction. We have given only the translation along x. Okay, so this is another boundary condition for me. Now I'll apply the load. Okay, the force should be along the selected direction. The direction should be again the top right plane. Plane got selected here. The faces these two along this direction. Let's take it as okay, let's consider 32,000 Newton. Okay, let's quickly mesh it. We'll use the fine mesh this time. Quickly use, okay, no issues. It should be 6 mm. Green check. Okay, so this is how the model is looking. The picture is here, perfect. Now let's run this analysis. Sorry, the material is not defined. We'll take the material again as the alloy steel. Apply. Now I can run this. Okay, now with this you could see the again the factor of safety BLF for this particular component is critical buckling load is 27 in the sense for this particular load case. This is for sure safe. If you want to see the animation, you can see it here. It is exactly buckling at that region. There's again a moment. So let's do one thing. We'll do one more simulation analysis. Let's see whether it is translating or not. So I'll simply click on green check. Now I'll come back here. I'll try to copy study. Nope. Okay, let's do one thing. So copy this and this, then simply paste here. Okay, these two are done. Materially apply the same. Now mesh it. The same mesh. I'd like to keep it as 6. Material is applied. The boundary conditions defined. Mesh is already done. Run this. Now you could see with respect to animation, if I see play, this is how it is moving. Okay, exactly along translation, right? And it should buckle somewhere here. So if I see the strain, plastic strain regions, this should be the critical one. Okay, here it is showing critical, so it is the failure region, but buckling should happen exactly at this region. But let's see in the buckling where exactly it is showing. Yeah, this is how it is showing. So as we see, if I try to set the animation clipping to true value, so it is exactly here. So this is the region it is going to buckle, and so it is not buckling at this particular load case, but if it should buckle. So if I just try to it is not a multiplication factor also, it should be somewhat more value in short. Okay, if you want to see the factor of safety, here only you'll get to know how much is the factor of safety for this component. Okay, automatic green check. This is minimum is 1, so in short fine. upper limit you can keep it as fine meshes. Let's see, multiplication factor, distributed area below. Okay, okay, it is 1. So in short, it is somewhere failing at this regions due to the geometry, but fine, no issues. But remaining everywhere it is fine. This is a geometry issue for information, guys. So if you want to see here, these are the regions it should actually buckle if we don't have the geometric issues. But yeah, now what I would like to do is I'd like to switch here one more model, multi-link, this one. So in this, so we'll simply try to apply one more fixture, sliding fixture. So on this face, advanced will take it. Okay, flat surface, this is the one. Like to keep this free. Okay, so with this, let's see how it is going to behave. Yes, so this is perfect. In the static also, if I see the displacement, we have applied the load, but we have given the, we didn't give any boundary condition here. So with respect to this particular boundary condition, it is trying to move in other direction. So let me just try to use some scale option here. So automatic, if I consider, it shows. Okay, yeah, here also it is showing this particular region. This is how it should actually uh, buckle. So these are the critical region. If you see the stress also, it is exactly very high here. It is 81 with respect to 500 Newton. This is fine for this one, but this is going to fail. If you apply the working boundary condition on this model, definitely it is going to fail. If you see the okay, let's say we can even get to know what is the buckling load factor for this. If I just apply 1 here, so we'll directly get to know. Okay, it is too much. So in short, it is going to withstand 146 kilonewton. So it is still a lot, but we can easily predict. So from this model, we are able to see where exactly it is buckling. So this is good for us, but static is also giving us the good result at the moment in short. So if I just see here, this is the region it is going to buckle. So yeah, now even if I go back to the model, if I just suppress this one and if I try to see, let's see how it is going to work now. Ideally it should buckle the same region, but let's see. Yes, perfect. You could see it is doing the same here. And if I switch back to this model, and here also if I try to run, let's assume we'll change this value. Instead of 500 Newton, let's take it to 50,000. Okay, okay, we'll run this. So 276, this is what the region is. And if I see the displacement, this is perfectly fine. Let me just animate this. This is perfect. It's exactly buckling here. Means displacement is showing like this. If it is going to buckle, if this model has the buckling failure, definitely it should fail here. And this is what we should observe here. Now let me just define the value here as 50,000 Newton. And let's run this. With respect to this load, let's see how this component is going to behave. Yeah, we have the load factor 15 greater than 1. So in short, this model is not going to buckle under the uh, what static conditions with respect to this particular load case. Okay, load factor we have it as 15, so it might be even considered the critical factor. Let's say we have the a buffer of load factor 3 or 4, even it is fine for this. Yeah, so this is all about the buckling analysis. I hope you got it. And yeah, it's in short tool we have used is SolidWorks simulation, but you just need to know what exactly the buckling analysis, so how we need to predict it, and how we need to see the buckling load factor. So from the structural analysis, whether we can able to predict it or not, if we are unable to if we are unable to predict whether we have the proper boundary conditions or not, that also we need to cross verify. Well, so in short, to summarize, we had gone through the basic structural analysis on the model. So again, to cross verify the structure and geometry and the displacement and the stress results. And after that, we had gone through the introduction to buckling analysis, and we see what and all the importance of the buckling analysis and why it is needed, and what is the linear and non-linear buckling and how we need to consider it. And in this particular example, we had considered one numerical problem, and we tried to implement it in the uh, SolidWorks simulation, and we got the approximate same answer. And we'll also try to work on a couple of models, the link, mechanical link in one of the chassis component, the suspension, and we had seen it. Okay, with respect to linear buckling, we could able to predict the buckling load factor. From the buckling load factor, we could judge whether the component is safe or not. Okay, and whatever the analysis we have done, it is all linear, and we should not trust this, but on an average 85% to 90% it is accurate. But when it comes to CAE field, we should try to have the accuracy. If you consider that into account, not trusting, so we need to do the non-linear buckling analysis. We can cover that in the upcoming sessions also. So I'll try to have one session on non-linear buckling analysis so that we can match these results and just give the final conclusion. Well, that's all from this session, guys. And if you're new for this particular webinar and to our YouTube channel, please do subscribe. And we have multiple social media platforms like the Instagram, Facebook, LinkedIn. Yeah, we also have created the WhatsApp group for the learners and the freshers and even the experienced candidates, where we try to give them the free course contents and also the job opportunities which are available in the current market. We try to regularly update over there. It's free of cost, we're not charging anything. Well, so you can even join that group, and the links are given in the description of this particular tutorial. Yeah, well, that's all from this webinar, guys. See you in the next session.